the router and all that. That's people missing, but we'll get rolling here anyhow. So let me start the recording. I'm getting better at doing it without getting reminded. Okay, so tonight we're going to be ending chapter 8. We're not going to be here very long tonight. There's not much left to do. It's just doing an improper integral, which you'll see isn't so bad. But sometimes when we do these improper integrals, we have a situation where we might need to use L'Hopital. So last night's homework or previous homework was all about Mr. L'Hopital. So anybody got homework questions? Section 8.7. Anything from there? Kayla won't be able to be here with us tonight, but she's still going to be available outside the class. She'll watch the recording, and she knows what she and I have been together a long time. She knows what I'm doing. She's just not going to be in the class with us tonight. So homework problems, L'Hopital, homework problems, L'Hopital. Anything? All right. Well, then let's move on to the end of chapter 8. So tonight, the integrals aren't really such a big deal, but we have to deal with this situation that comes up. So we have improper integrals. Now the title of this section is just improper integrals, but I'm going to throw in this extra word. Because improper integral refers to a definite integral. So I'm just going to do some examples. So here's our first example. We're going to look at the integral of 1 over x to the 4th dx. And that's not a very difficult looking integral at all. And here's what makes this improper. So we're going to start at 1, and we're going up to the top number of b. Now that b isn't going to be specified. However, we're just going to let b get really, really big. So here's the formal way to write this. So we're looking at the limit as b goes to infinity. So this is the correct way to write. Oh, Jacob's coming in. Hang on a minute. Hold on just a second till Jakob gets here. All right. So this is the correct way to write an improper integral, but this is pretty much the last time I'm going to do it. So we have a shortcut. Instead of writing this, we're just going to pop the infinity sign up here, but it really means all of this. All right, so first we ignore all of that and we just do the integral. So I'm going to rewrite it from 1, and now I'm just going to throw the infinity sign up there. Rewrite this as x to the minus 4 dx. And now we do that integral. And so we add 1 to the exponent. So that gives us -3. And we divide by the new exponent, which is -1/3. So that's the end of the integral. And then we go from 0 to infinity. Now we deal with the improper part. So the top goes in first. So this gives us -1/3 infinity to the -3rd power minus -1/3 1 to the -3 power. So over here, this part, that just becomes +1/3. That's a constant, no big deal. But now we have to figure out, where does this go? So now we have an occasion where, so infinity is not a number. So my advice would be, for all of these problems, if you have a negative exponent, get rid of it. They can fool you. So I'm going to get rid of this negative exponent. And I'm going to write this as -1 over 3 times infinity cubed. So what's infinity cubed? Not really a number, but what happens if you take infinity and raise it to the 3rd power?
Still infinity.
Still infinity. So what happens here, we have -1. We have -1 over infinity. So we have a constant on the top. And in the fraction, as the denominator gets really, really big, the fraction becomes very, very, very small. So if your denominator becomes infinitely big, what does the fraction become?
0.
Yep, becomes 0. So the limit as b goes to -3, as b goes to infinity, that limit is 0. Never get there, but that's the limit. And that makes this the solution. So the answer to this improper integral is +1/3. So everything except this part is familiar. In fact, that's a Calc 1 integral, right? And it's a really simple one. So let's see what all of this means here for a little bit. So we have this improper integral. So what does this answer actually mean? Oh, we got some people coming in here. Hang on.
I have a quick question before you erase that.
Yeah, go ahead, Jakob.
It was from b to infinity, so you switched it from 1 to b?
Well, no. The proper way to write this is we're going to start on the x-axis at x equals 1, and we're going to integrate to the end of the x-axis, which doesn't exist. So b is this number that's bigger than 1, and we're going to look at what happens as b just becomes infinitely large. So this piece right here is the official correct way to write the integral. But even in the textbook, instead of writing all this, we just pop the infinity sign up here, which is grammatically wrong, but it's just the way we all do it. Is that?
And then it becomes from 1 to infinity or 0 to infinity?
Oh, I'm sorry, this should be a 1. Thank you. I put the 1 here. I have that part right. I have no idea.
Yeah, that's why I was all confused. Okay.
I have no idea why I wrote 0 there.
And why don't we start by the smallest number after 0?
I'm not sure what you mean. Oh, because this problem says begin at 1.
Oh, okay.
This is part of the original problem, right? If we started with a 0 here, we'd have a problem because you can't put 0 in here. So that would be a different kind of improper integral. But I just said we're starting at 1. So that's why we're starting at 1, because I said so. So does that clear up your question?
So essentially b is 1?
No, b is a bigger number than you can imagine. So b is going all the way to infinity. But technically speaking, we can't put infinity up here because infinity isn't a number. So you have to write it this way. And the book does one example like that, and then they just start putting infinities up there. So it's just a style thing. All right, so let's see what this means. Here's one way to interpret this. Oh, so well, first of all, before I do that, if x is bigger than 0, the graph of y equals 1 over x, that graph looks kind of like that, right? And the x-axis just keeps going this way. And it just goes forever. What does the graph of 1 over x to the 4th look like? And x is bigger than 0. So that's 1 over x, more or less. What does 1 over x to the 4th look like? What does that how does that exponent change this shape? Well, when x is a big number, this makes it bigger faster. And when x is a little number, it makes it smaller. So what it does is it makes this graph, whoops, bad. It makes that graph even sharper and steeper. So what we've just determined is even though this function never touches the x-axis because this can never equal 0, it just keeps getting closer and closer to closer. It's a horizontal asymptote. But if we go all the way out to infinity, the area of that underneath that curve is exactly 1/3, which is kind of hard to imagine. How can it be an area when it never closes off at the end? You can always leak out. And sometimes it doesn't. So that's one way to interpret this as area. So try another well, I'm going to do another example now. Let's take this one. Let's do the integral of x over. Wait a minute. Do I want to do this one first? Hold on a minute. Oh, let's do this one first. We're going to do 1 over the cube root of x dx. And so, Yakov, I'm just going to make up a starting number here. I'm just going to say 8. So from 8, and we're going to go all the way to infinity. This is what makes it improper. So I'm not writing the limit as b, and I'm not putting b up there. So first we'll rewrite this. 8 to, oh, okay, well this is going to be nerdy, but I just realized we're starting at 8, and we're going to, I just turned the 8 sideways and make an infinity symbol. Huh. Well, that was pretty nerdy, but whatever. So this is x to the negative 1/3 power dx. So I just wrote this algebraically.
So wouldn't the answer just be 90 degrees?
Wouldn't what?
The answer just be 90 degrees.
That was pretty good. I like that one. I like that. That was, yeah. Oh, you win. You win that whole round. Oh, as long as we're on stupid jokes. What did 0 say to 8? What did 0 say to 8? Nice belt. Oh, nice. Yeah, that one takes a little minute to think about it, right? You squeeze that in here. All right, back to real math. So now, to do this integral, we add 1 to the exponent. Negative 1/3 plus 1 is positive 2/3. And we divide by the new exponent, 3/2, and we go from 8 to infinity. So again, Calc 1 integral. Top number goes in first. We get 2/3 infinity to the, 3/2. 3/2 to the 2/3 power minus 3/2 8 to the 2/3 power. So over here, the cube root of 8 is 2. 2 to the second is 4. 4 times 3 is 12 divided by 2, so that turns out to be 6. But what happens over here? This 3/2 has no effect on it. What happens when we have infinity and raise it to the positive 2/3 power? Does it get bigger or smaller? I'm sorry, Rebecca, what? No, we're raising infinity to a positive power, so this whole thing, that whole thing goes to infinity, right? So the cube root of infinity is infinity, and infinity squared is infinity, and infinity times 3/2 is infinity. So this whole answer, we say that this diverges because infinity minus 6 is still infinity. So this whole answer is infinite. So if we take the graph of 1 over cube root of x and we try to calculate the area underneath the graph from 8 to infinity, there's an infinite amount of area there. So when your answer comes out to be infinity, the term is diverges. And let's think of diverge here. We think of diverge as we go along, things just expand. That's kind of what it means to diverge, and off it goes to infinity. On the last problem, our answer was positive 1/3, and I'll write this down in a minute. If you have an answer that's a number, then you converge. And I'll give you an example in just a minute, but we okay? Questions on this particular problem yet? All right, so here's what happens. The last two problems had this logical structure. All right, so we have 1 over x to this exponent p, and just think of p as the word power. Now, if p is bigger than 1, then that integral will converge, and that just means a finite solution. So x to the 1.1, your answer is going to be a number. X to the 1.2, your answer will be a number. X to the third, x to the fourth, x to the fifth, your answer is going to be a number because the infinity part goes to 0. If p is less than or equal to 1, then you diverge, which basically means you have your answer is infinity, which is not a number at all. So that's for things that look like this, which come up a lot. And so one thing you might want to ask is, always in math, so what? What's this have to do with real life? Well, here's a way to think about what it means to go off to infinity. You can't really get there, but imagine if you're doing some kind of chemistry experiment, or you're doing some kind of physics or biological experiment, and you set a process into motion. You mix a whole bunch of chemicals together and start the clock. Or you do something in a physics lab with pressure and stress on metals. Or you introduce an agent into a biological system like an antivirus or an antibiotic or a medication. And so in real world applications, you want to think of going to infinity as once you begin that process, never turn it off. Right? So you mix a bunch of chemicals together and you stand back and you watch what happens if you never do that. Or you introduce medication into a biological organism and then just leave it there forever, right? So both of these things have two different meanings. If your system converges, that essentially means you become stable, right? You're converging to a stable point, like an asymptote. If your system diverges, well, let me ask you a question like this. Suppose you have a sealed container and you introduce something that causes energy to start to come out in that system. Within that closed system, what happens if the energy increases and never stops increasing? You're in a closed sealed container. What happens if that energy just keeps growing and growing and growing and growing? Right? It's never going to converge. It's never going to be stable. The energy just keeps getting more and more and more. What do you think would happen?
It's a lot of like pressure built up.
Yeah, but the pressure is never going to stop building up.
That's a problem.
Well, is it? You might want it. So what happens if you're in a sealed container and the pressure never stops increasing? At some point, what's going to happen?
It'll explode.
It will explode. You've just built a bomb. no matter what kind of sealed container that you put in it, eventually pressure and energy is going to outdo any strength of material and you explode. So you can think of that as diverging. It's just off to infinity and boom. Right? So that's one way to think of this stuff that feels kind of abstract. So it does come up in practical things. I don't know what all your backgrounds are, but I'm assuming a lot of you have heard about a thing called a black hole, right? So black holes tend to exist in the middle of the galaxies, and the galaxies are all swirling around. They're all going down the drain. The black hole is like a drain, and all the stars and galaxies, including us, we're just circling the drain and we're getting into that black hole. That black hole has infinite gravity, and so it diverges and it just pulls us all down into there, and that's it, game over. So there are some practical things to this. All right, let's try another example. So x over e to the negative x power. Let's start at 0 and go to infinity. Okay. Well, the first thing I'm going to do is rewrite this. I don't like negative exponents. They cause all kinds of confusion. Negative exponents, you're down when you're supposed to be up. You're up when you're supposed to be down. So 0 to infinity. I'll rewrite this as x e to the x dx. Okay. Now, whenever we do definite integrals, you ignore this stuff. We just do the integral. How do we do that integral?
By parts.
Yeah, by parts. See, I snuck in a little review question here. So here we have by parts. So we'll let u equal x, dv equal e to the x dx, and du then equals dx, and v is equal to the integral of e to the x, which is e to the x. So by parts, it's uv minus the integral of v du. So u times v is x e to the x. And then we get minus the integral of v dx, which is e to the x dx. And all of this is from 0 to infinity. So always with by parts, there's another integral to do. Sometimes more than one, right? So this becomes x e to the x. The integral of negative e to the x is negative e to the x. And we're going from 0 to infinity. Now we put the numbers in there. We get infinity times e to the infinity minus e to the infinity. And then minus, we put zeros in here and we get negative 1. This is just a constant, doesn't matter. But what's happening here? Well, we have infinity and nothing's making that go away. And this infinity isn't in the denominator. So all of this goes to infinity. So we get infinity plus 1, which is still infinity. And so this diverges. But this graph, x e to the x, that's an increase. It's going up really, really fast. And it's never going to come back down again. So here's
what does the negative e to infinity become?
E to the infinity is infinity, right?
Yeah.
So we have infinity times this infinity minus that infinity. We still have infinity.
Infinity minus infinity is infinity?
Yeah, but this this isn't infinity, so we could factor this out. Infinity minus infinity is not always infinity. Sometimes it can be infinity. Let's factor this out. You see I factored out the e to the infinity? You okay?
Yeah.
So infinity minus 1, that's infinity. So this is infinity times this infinity, and the whole thing, that's it, still infinity.
What if I don't factor it out? Then I get infinity times infinity, which is infinity, and then I get minus infinity.
Yeah, but this infinity is bigger. And there we go with that whole different thing, right? Because algebraically, these are the same. So this is infinity times this infinity, and then we subtract that infinity back off, but we're still left with this one, and the whole thing is still infinity. So pretty much what it comes down to is this.
So it really depends on which order you do it in.
Well, if you do just this one, if you just look at this, you're right. You get infinity minus infinity. That's indeterminate because we don't know what that can equal, right? So you can't make any conclusion if you leave it in that form. Infinity minus infinity might be 0. Infinity minus infinity could be infinity. Infinity minus infinity can equal 1. It's an indeterminate form. But once we factor it out this way, this now gives us infinity times infinity, and that's indisputably infinity because they're both positive. Does that help a little bit?
Yeah, I guess that's only if you choose to factor it out.
But you have to. You can't leave it like this because you can't make any determination at this point. Infinity minus infinity is like 0 over 0 or infinity over infinity. We don't know what that is. But by manipulating it algebraically, now I can see that I get this form, which is not indeterminate. That is infinity. So you have to manipulate this one. You can't do anything with that.
I just find it funny how you can get different answers based on how you manipulate it.
Yeah. Wait till we get to chapter 9. It's all about this stuff. This is like the lead into chapter 9 a little bit. All right, so this diverges. Let's try another one. Let's try this. Let's do 1 over x times the ln of x dx, and we'll go from 0 up, can't go to 0, sorry. We'll go from e to infinity. So 1 over x times ln x, and we're going to go from e to infinity. So now the question becomes, ignore this. How do we do that integral? So that's, well, we've seen some of this in chapter 8. You might have even seen a one like this in Calc 1. How do we do that integral?
Interest or U substitution?
Yep, we do U substitution. Nice one. So we let U equal ln x. We let and then du becomes 1 over x dx, which we have 1 over x dx. So this integral becomes 1 over u du. But I can't put e and infinity here because those are x values. But I can convert them. There's my translation right here. When x is e, what is u? If x is e, what is u? What's the ln of e?
1.
1, nice. So we go to 1. And now, when x is infinity, what's u? You have the ln of infinity, and that's infinity, and I'll explain that in just a minute. So now we can work this way. So the integral of 1 over u is the ln of u, and we're going from 1 to infinity. So that gives us the ln of infinity minus the ln of 1, which is equal to just the ln of infinity minus 0, because the ln of 1 is 0. So our answer here is the ln of infinity. Is that a number? Does that go to 0, or is that infinite?
Infinity?
Yep, this goes to infinity. This diverges. This integral just explodes up and just becomes infinite. There is no finite solution to there. It's just infinity. So this diverges. And I want to show you a little bit about why we know that. Because chemistry, biology, physics, finance, when I send out some stuff tonight, there's some questions about an account that has a certain interest rate return, and how long does it take you to double your money, and what happens if you leave your money in there forever. So you're going to see some applications of all this kind of stuff. So let's take a look at, wow. So first of all, any questions on this part? All right, let's take a look at the ln function. They come up a lot, even if you don't think they do. So y equals the ln of x. Well, first of all, x has to be bigger than 0. This is called the argument of the ln. This has to be a positive number. Can't be 0, can't be negative, doesn't exist. So the ln function looks like this. And it just keeps going down here to negative infinity. If x is bigger than 1, the value of y is a positive number. When x is equal to 1, y is 0, because the ln of 1 is 0. It's sitting right there on the x-axis. When x is a number smaller than 1 but positive, the ln just keeps getting smaller and smaller and smaller. So the question is, how do we know that the ln just keeps getting bigger and bigger? ln is always increasing. And that means as x goes to infinity, the ln of x also goes to infinity, just a bit slower. But how do we know that for sure? How do we know that at some point it doesn't start curving down again? How can we figure that out? So I'm going to take you back to some stuff from Calc 1. So y is equal to the ln of x. What's the derivative of y? What's the derivative of y?
1 over x.
1 over x. All right. Now, the derivative measures how fast something is changing. The derivative also tells us what direction it's going in. Since x has to be a number bigger than 0, x is always positive. That means 1 over x is also always, if x is always positive, 1 over x is also always positive. So because x is bigger than 0, y prime is also positive. What does it, when a derivative is positive, what does that tell us about the function?
It's always increasing?
It's increasing. And since x, that was really nice, Michaela. And since x is positive, the derivative is always positive, which means that function is always increasing. Now, as x gets bigger and bigger, this number gets smaller and smaller, but it stays positive. So x is always increasing, but it goes slower and slower and slower as x, so it kind of curls over a little bit, but it's always increasing. So here's a case where you know something's increasing or decreasing by looking at the derivative. If the derivative is negative, it's going down. Derivative positive, it's going up. If the derivative is 0, it's just going in a horizontal direction and the y values aren't changing at all. So that's how improper integrals work. The integral part isn't so bad. I mean, we recognize tonight, oh, that's a by parts problem. That's a U substitution problem. And let me see, we have not used L'Hopital yet. So I'm going to do one more example where we are required to do L'Hopital. Unless anybody's got some questions about this. So not every problem requires L'Hopital, but you got to be ready when it comes up. Okay. Last example of this, and then when I'm done with this, I'm just going to spend a few minutes talking about something called a differential equation, which you've already been solving, by the way. Every time you do an integral, you solve the differential equation. So let's look at this one. Oops, not mine. Let's do x over e to the 2x dx. And we'll go from 0 to infinity. All right, so first we have to rewrite this. So we go from 0 to infinity. We get x e to the negative 2x. And we know what method to use on this one, just like the previous problem. So we integrate by parts. But this problem is different because we got a negative exponent. The 2 is just irrelevant. It's just noise. So u is equal to x. dv is equal to e to the negative 2x dx. du is equal to dx. And v is equal to negative 1/2 e to the negative 2x. So now we go over here. We have uv minus the integral of v du. So u times v is negative x e to the negative 2x over 2. In the formula for by parts, there's a negative sign, but this makes it a positive sign. So we get plus 1/2 the integral of e to the negative 2x dx. And all of this goes from 0 to infinity. And I'll pause there just for a second. Oh, geez, Mariana. Hold on. I hope she wasn't here long. Hold on a minute. Simple. Hold on a minute. Mariana, hi. I hope you weren't waiting long. Are you there?
Hi. Yeah, I wasn't waiting long.
Oh, because I concentrated in writing and suddenly I saw your name and I was like, oh no, I hope she hasn't.
Yeah, I was running late.
Oh, no, that's okay. I just felt bad. You might have been like sitting there waiting for me to like notice.
Yeah,
you.
you're okay. You're okay. Thank you.
Yeah, you're welcome. Okay, I thought maybe somebody just had a question. Oh, and Mariana, everything's being recorded.
Okay, thank you.
Yep. I thought somebody had a question just a second ago. No, all right, must be imagining things. Okay, so we get negative x e to the negative 2x over 2. And now this integral becomes minus 1/4 e to the negative 2x, and all from 0 to infinity. So Mariana, I only did like 3 other examples. There isn't a lot going on here. So this is just stuff we've done in chapter 8 before. What's different tonight is we have this infinity up here that we have to figure out. And in this problem, it's going to end up that we need L'Hopital's rule from last time. All right. So anybody got questions so far about what I've done here? All right, let's plug numbers in. Well, infinity is not a number. Keep that in mind. So this becomes, now my advice, infinity or not, is get rid of negative exponents. They can make you think you're going up when you're actually going down and other way around. So I'm going to write this as negative x over e to the 2 times e to the positive 2x minus 1 over 4 times e to the positive 2x. All right, so now we plug infinity in, and we get negative infinity, and e to the 2 times infinity is infinity. Then we get minus 1 over 4 times infinity, minus, now we put the 0 in here. So we have a 0 on the top, that's just 0. And then we get minus 1 over 4. So those are the numbers all in place. And I'll pause here just for a second. So has anybody got a question yet? All right, well, this part, that just becomes positive 1/4. And this, we have a constant on the top and infinity on the bottom, and 4 times infinity is infinity. So 1 over infinity is what?
Practically 0.
Well, yeah, if you actually get to infinity, it does equal 0, but we never get there. So this, now remember, in my sloppy writing, there's really a limit sitting out in front here. So this would be the limit as b goes to infinity. So this is 0. But this, oh, forget the negative sign. It's L'Hopital, right? It's infinity over infinity. So here, so this is our good old friend, our good old friend Guillaume. So we have to use L'Hopital. So this would be the limit as, let's see, how do I want to write this? As x goes to infinity of negative x over 2 times e to the 2x. I think that's what that piece was. Am I right? Yeah, I'm right. All right. If we put infinity over here, we get negative infinity over negative infinity. And that means we can use L'Hopital. So by L'Hopital, we get the limit as x goes to infinity. The derivative of the top is negative 1. What's the derivative of the bottom? What's the derivative of all of this?
4e to the 2x?
Yep, 4e to the 2x. Oh, that was going way back, wasn't it? You've been doing integrals so long, forgot how to do derivatives. Now, when we put infinity in here, there is no x up here. So we get negative 1 over infinity. So this just goes to 0. So up here we get 0 minus 0. And the final answer is 1/4. So our original interval converged to a finite number. So the area under the curve from wherever we went, 0 to infinity, is exactly 1/4. So this is where L'Hopital may or may not, on some of the homework problems, that pop up in the end when you're plugging numbers in. All right. Questions about that? Okay, so that's pretty much the end of chapter 8. So chapter 8, we've got by parts, trig integrals, trig sub, partial fractions, L'Hopital, and improper integrals. So I'll be sending out, besides just a couple of these problems, I'll be sending out some review problems as well tonight for you to work on over the next thing. On our class on Tuesday night, we'll do a final review of all of this stuff. And then I know a bunch of you have some tests later this week. I know there's a physics test coming up on Wednesday or Thursday. And I think there's a couple of other things coming up. So after our class on this Tuesday, I will send out the chapter 8 test, and it'll be due sometime on Wednesday, and that'll get it out of the way for those of you who have tests at the end of next week. You know, it seems like there's this big plot where everybody has their tests at the same time, and there really isn't. It just happens to work out that everybody gets to a point where it's time to have a test. It just happens to work out that way. So let me just leave you off with one thing. There'll be a couple of homework problems on the review sheet that I'm going to send out, and something called a differential equation. So I know some of you are headed there. So every time you do an integral, if you do an integral like 3x squared dx, you should be able to do that one in your head, by the way. That's a differential equation. And you might think to yourself, how can that even be an equation? There's no equal sign. And it's because the rest of the problem has actually been left out. So if you start with a derivative, if we say that the derivative dy dx is equal to 3x squared, right? That's a differential equation. It's an equation, and these two things are called differentials. So I'll get to this in a minute, and why these are, well, I'll get to why these are important in a minute. So I'm going to multiply the dx to the other side. I'm separating the differentials. So there's a differential equation. The goal of a differential equation is to figure out what y is. So in algebra, the solution to an equation is generally a number. In differential equations, the solution is another function. So now, how can I get a y out of dy? How can I extract a y from dy?
Integrate?
We integrate. So if I integrate this side, it's algebra, I have to integrate this side. And the integral of 1 dy is y. And for this particular problem, we know that y is x cubed plus c. So this is the solution to my original differential equation. So all the times you've been doing integrals, you've just seen that little piece. But there's a differential equation going on here. And why differential equations are important, they are how we observe the real world. So when we say that if a derivative is equal to some function, okay? This is the first derivative, so this is something called a first order derivative. You can also have second, third, fourth, and fifth derivatives. So anytime you measure something in life, anytime, whether you're in a chemistry lab, a biology lab, you're looking at the stock market, you're looking at how money moves around within a company, and you look at something at a particular point in time, and you measure where it is, and then at another point in time, you measure it again, and you see how much something has changed from point 1 to point 2. When we measure things in life over time, you are measuring how fast that thing has changed. And a derivative is a measure of how fast something is changing. So if you keep doing all these measurements of something changing over time, if you're engineering and scientists, you build up a differential, you build up a function that predicts how fast something is changing at any point in time. So how fast will this be changing tomorrow? How fast is this stock price moving in 3 hours from now? By solving this differential equation, do it by integration. Now, this function gives you the underlying principle of how that change is happening at any time, and you can predict forwards and backwards. So ultimately, getting to the differential equations is when you can really start modeling real world events. So that's kind of where we're going with the integration here. So when I send out the review sheet in just a little while, I'll upload this recording. Let me stop the recording. Stop it. If I stop it, it keeps the file sizes smaller so I can keep more up there for you. There'll be homework about improper integrals. There's like 6 or 7 homework problems. They're all pretty much like I did tonight. And then there will be a file called Chapter 8 Review. So you're going to see like 10 integrals on there, and you just do them. But I haven't told you what methods to use. You got to figure that out. And then on the second page, there's three problems involving something like this. They're all integration. And we will cover everything on Tuesday. Or you can email me over the weekend with questions if you want. So I'm done talking. Anybody got any questions or anything?
I just have a question about discrete, actually.
Oh, okay.
Do you think the exam's going to be next week for discrete?
Late next week, because I know you got a bunch of other tests going on.
Okay, cool. So do you think it's going to be on like different days of the calc exam?
Oh yeah. I'm definitely, and I'm sorry it's happening at the same time again. I don't know. So Tuesday in discrete, we're going to have a review, but I'm not going to send you the test until like Thursday or Friday.
Gotcha.
Still on Thursday, we're going to do something new in discrete, but
Yeah.
I know you got physics and calc. I thought I can't have you do this. So I'm going to, for the discrete folks, I think there's 3 of you in here. It's not going to be till Thursday or Friday.
Gotcha. Thank you.
Yeah, you're welcome. You're welcome. Anybody else got anything?
I do not envy having 3 tests in 1 week.
Yeah, and like I
2 is
said,
enough.
it always works out that way. I don't know what it is. One of my students said this morning, it's just a damn conspiracy among all you professors. And my response was, no, there's way too much conspiracy crap going on in the world these days. You don't need one more. It just happens to work out that way. I don't know why.
I have a conspiracy that conspiracy is infinite and therefore.
Yeah, all conspiracy theories are a conspiracy theory, right? So that's it for us tonight, folks. I do know that the next 3 days, it's going to be wonderful and sunny and warm. Even if you've got lots of studying and work to do, try to get outside. It'll be good for you. Go for a walk in the woods, all right? So I'll see you all back here on Tuesday. I'm going to upload everything in like the next 15 or 20 minutes. And have a great weekend. I'll see you back on Tuesday.
Thank you.
Take care.
Too.
All right,
Bye, thank you.
everybody.
Thank you.
Bye-bye.